Okay, so let's start. So this seminar will be about a research project we had at the University of Dundee, which is about the design of rock anchors for offshore applications. So obviously I was not alone, so I worked with Michael Brown at the University of Dundee, and this was in collaboration with a company which is SME, Sustainable Marine Energy. Adam, Andy, and Nick are from this company, and this was co-funded by the Scottish Aquaculture Innovation Centre. So to start with, I would like to put everyone on the map. So if you don't know where Dundee is in Scotland. Here, this is the sunniest city of Scotland, and this is where the university is. SME is based in Edinburgh, and the Scottish Aquaculture Innovation Centre is from Stirling. So you have some nice pictures of Scotland here. On the other hand, Optum, the headquarters are in Copenhagen in Denmark. And myself, although I'm working in the University of Dundee, I am from Liège in Belgium. So this is quite finally a European project, even if it is very Scottish based. So what's the context for this work? The main context is mainly about aquaculture. Aquaculture is a big thing in Scotland with a lot of jobs and a lot of money made out of it. And 170,000 tons of farmed salmon per year. But there are plans to expand this further and to deploy aquaculture farms in more energetic sites further from the coast and in deeper water. But also, what we are studying here can be applied to tidal turbines, because so this is quite different from the usual wind turbines, but you just use the energy of the tides to generate some electric power. And you also need to be in very energetic sites. So you need to develop larger and stronger anchors. And this is where the company comes with a new design of an anchor, which is actually self-drilling. So you can see, here at the bottom, the part of the anchor that drills the hole in which the anchor is embedded, but there is no grouting. So you just move this part up, which expands the fingers of the anchor, and everything is kept in place. The good point is that this is a rapid installation. There is low noise, since this is rotational drilling. There is no grouting, so you can remove and reuse the anchor, which is a very good point. The downside of it is that the common practice, the common technology with rock anchors is to use grouted anchors. For instance, you have these post-tension anchors here that are used for dams, for instance. In this case, you just drill a hole, put the steel tendon here, which is the anchor, add some grouting. So how can this type of anchor fail? It can fail if the steel tendon fails, or at the interface between the steel tendon and the grouting, or at the interface between the grout and the rock. And these are the most probable anchor failures. There is a fourth mode, which is actually a failure in the rock, which is adjacent to the anchor. But in practice, this is not really encountered. And the guidance for this failure in the rock is that you should consider a weight of a rock cone here that is moving upward with the anchor. And that's it. But now, if we consider our groutless anchor, which is locked at the bottom here, there is no grouting, so there won't be any failure between the grouting and the rock. And there are two modes of failure, which is either the anchor fails or there is a failure in the rock. So the problem is we don't have a lot of guidance about this, because this is not something that is really encountered in practice. There are some models which exist. Simplified analytical model for axial mechanism. So you just have an anchor. This has been developed for grouted anchors, but still this is related to the failure in the rock. Usually what is assumed is that we have a conical shape, or a sort of a cone of rock moving upwards. Here are three different analytical models which have 3 different shapes of this shallow wedge moving upwards. The other hypothesis which is usually made is that you have a stress state here along the failure mechanism. All of these models usually use the Hooke-Brown failure model, constitutive law, let's say. And depending on which model you consider here, we consider different stress states. The first one considers that everything is at this point, so it's a tensile failure everywhere. This one consider we have compression everywhere, and this one consider we have tension and shearing at the same time. So 3 different models, 3 different sets of hypotheses, and we don't know which one is the real one actually. So this is why we had this project where actually the objective was to study the self-drilling groutless anchors, and especially to identify the actual failure mechanism, and so the shape, and what is the stress state at failure. And then when we know this, we can compare with the existing analytical criteria and maybe modify them. And obviously, these existing criteria are quite simple, so we should try to find a way to add some new parameters in the design. And finally, we would like to extend this study of the failure mechanism to combine horizontal vertical loading, so incline loading. And this is why we used Optum, because Optum has many advantages for this specific purpose. It is designed to calculate and to do some limit analysis, so to identify failure mechanisms. It is quite efficient and fast, so it's quite easy to undertake some parametric studies, and it has the Hooke-Brown model embedded in it, so we can use it directly and compare directly to analytical methods. And it has a robust interface element, which is quite useful for this problem, and it exists in 2D and 3D. So let's start with the first thing we studied was the axial failure mechanism. So we studied a simplified problem because we have seen the anchor has quite a complicated design. So what we did is we modeled the drilled hole because it is there, and we just modeled the part of the anchor that actually is restrained into the rock, so the inclined finger part. So there are several things to consider here: the diameter of the anchor, the height of the anchor, its embedment depth, which will be capital H, the interface properties, and we apply a unit pressure, and then we go through Optum, and Optum finds a multiplier applied to this unit pressure, which gives finally the maximum capacity. So yeah, last thing, the anchor is modeled as a rigid body. And let's go. So I just would like to spend a few seconds on the Hooke-Brown model. I won't go through all the equations, it's pointless, but I just want to point out that there are 2 different parameters here, which are the uniaxial strength of the intact rock and another sort of fitting parameter for the intact rock. And there is something I will talk about later. There is the GSI, which is the geological strength index, which is actually something that enables us to move from the intact rock properties to the rock mass properties. So I won't go into the details of how do we calculate this, but there is an underlying hypothesis, which is that if we have a failure through this modified Hooke-Brown model, the failure process must be dominated by rock sliding or rotation of rock blocks. So this is a shearing failure mechanism. It's not like crack propagation. So in this project, we investigated 3 types of rock just to have to span over different uniaxial strengths. So we have a basalt, a very weak chalk, and a sandstone. So now we can start with the Optum simulation. The first question is, how many elements do we need? So we can do something basic. We have the geometry, and there is an option to increase the number of elements, and this is an adaptive meshing, so it's done automatically. And you can see that if you increase the number of elements, we have the load multiplier that is calculated by the lower bound solution and the upper bound solution. So we have the convergence, obviously, and they meet here in the middle. So I normalize everything here with the load multiplier, but after roughly 4,000 elements, both solutions are plus or minus 5%. So it's totally acceptable for me, and I just kept this number of elements to make the simulation quicker. So what does the failure mechanism look like for these simulations? So I just picked a few snapshots as the number of elements increases. You can see here few elements. You can already see that something is happening here. And as you increase the number of elements, there is a refinement. And this is the geometry I finally selected here. You can see that this is very refined. So there is the failure mechanism. So how does it look like? If we plot the shear strain, this is what we can observe. And as I said before, we have a wedge. So this is consistent with previous studies of failure wedge in uplift. Although this is not a straight line, this is still a wedge. So the guideline said, oh, this cone should be between 60 and 90 degrees opening, so 30 degrees for half of the cone. What we have is actually something around 55 degrees, and it's not a straight line, and there seems to be a sort of inflection point here. I will come back to this later. So this is already some interesting information. We have a difference in the shape of the failure mechanism with respect to what we were supposed to use. Now, I said there are two hypotheses. There are the shape of the failure mechanism, but there is a stress state as well. So something you can do in Optum is just you click on some point in the results and you have all of this information. And you have the principal stress here. So actually, if you click at several points, you can collect this principal stress state, and then you can report it on a graph. And this was the Hook-Brown, the black line was the Hook-Brown model that was supposed to be used, and all the points that are all along this are well located on this envelope. So we have a failure, and this corresponds to the Hook-Brown parameters we have used. I didn't doubt about it, but it's worth verifying sometime that we are obtaining what we are doing, what we want to do. But then if we go back to the hypotheses at the beginning, there were three different methods. One saying, oh, it's compression and shearing. One saying it's tension and shearing. And the last one saying, oh, it's pure tension. And actually, it's a mix of these two here. We have some points along the failure mechanism that are subjected to compression and shearing, and some points that are subjected to tension and shearing. So where are they located? If you trace them, all this stress here as a function of the distance from the axis of symmetry, here close to the anchor, we have quite large stresses. The stress magnitude is very large, let's say. And if we go further away in the far field, then the magnitude is much lower, which means that these points here are those close to the anchor, while these points here are those which are further away. And why do we observe this? Simply because there is an interaction between the stress field in the vicinity of the anchor and the failure mechanism. So this is the stress distribution and the vertical stress, the horizontal stress and the vertical stress distribution around the anchor. And this is the failure mechanism. And since we are very close to the anchor here, the stress is very large in this vicinity. So the normal stress along this failure mechanism is large, and then the shear we can mobilize there is much larger as well. So there is an interaction. And we cannot simply use the stress state in the rock before the anchor is loaded to calculate the final capacity. We need to take into account this interaction. So this is for the stress state. Now, I mentioned that the GSI is quite important to move from the intact rock to the rock mass. So the question would be, how does this failure mechanism change with the GSI? And actually, this GSI changes the apparent friction angle of the rock and changes the properties. So depending on the GSI, we have something, it was 55 degrees here, and something that becomes wider. The failure mechanism becomes wider as the GSI changes. So it's not a single value that we should consider for this failure mechanism. It's not even a single value for a given material, but it should depend as well on this GSI. Now, something more interesting is the depth effect, because obviously if you have an anchor, if the capacity you have is not sufficient, then you just want to install it deeper, because usually the deeper you go, the larger is the capacity. So let's have a look at the failure mechanism as you go deeper. This is a very shallow failure mechanism. It's almost a straight line. If you go a bit deeper, it becomes nonlinear. It's more the case I've just described before. But if you go very deep, then we change totally the failure mechanism. We don't have a cone anymore, but we have something very local here with a block of rock that is actually crushed and moved. And we don't have this wedge anymore. So this was never considered in the analytical models that we used before. And I will show you that this has implications on the design. So now, if I collect the data, the position of this failure mechanism for all of the different rock types that we investigated, as a function of the GSI and as a function of the normalized depths here, you can see that there are plenty of different shapes of this failure mechanism. If you kind of normalize a normalization, you can somehow collapse them onto a sort of backbone curve, but still there are some great variations. So I just wanted to show that although the guidance is quite simple, the reality is much more complicated than this. So this is great for research, let's say, but what if I want to design my anchor with Optum actually? So I would say this is quite easy. You just start with Optum, you just create your different geometries, few clicks, then you choose the type of analysis. In the following, I will always show results of the limit analysis, and I use only lower bound element type, because I don't do for all simulations twice the simulation upper and lower. I just say, oh, I have enough elements, I've tested it before, so the lower bound is quite sufficient for what I'm doing. And then you run the software and you have the load multiplier here that you can collect here, or you use the embedded result tools. And the good point is that you can create a lot of different simulations, click on run, and run it during the evening or the night if you want. And when you arrive in the morning, you have all the results to post-process. So now let's continue with the anchor design. If you do this for different geometries, so I have a given anchor geometry, but I embedded it at different relative depths. So this is the relative embedment depth. So the embedment height divided by the base of the anchor, so the diameter of the anchor base. And we have here 3 different rock types, and for each rock type you have a different GSI that corresponds to different rock mass properties. So all these results are normalized. So you pick up the load multiplier and just divide this load multiplier for all simulations by this load multiplier here, which corresponds to the chalk at the deepest embedment ratio. Each marker in this figure corresponds to actually to a single simulation. So if you have a bit of time and you want to design your anchor, the easiest way is to run a large number of simulations, create some design charts, and then when you have to design your anchor again, it's just interpolation between all these points. So obviously, the weaker the rock was, the weaker the capacity is. So we have 1.5 here, 50 and 150. The basalt being the stronger rock, it gives you the stronger capacity. What is interesting in this figure is that you can see that as you increase the embedment of the anchor, you increase the capacity, which makes total sense. But beyond a certain depth, the capacity is capped. And actually this corresponds to what I've just shown before, where you have a change from the shallow fellow mechanism to the local fellow mechanism. This local fellow mechanism doesn't depend on the depth. So beyond a certain depth, you can go deeper and deeper and deeper. You won't have any increase in capacity. And so this is quite important, and I will show you on the next slide. The other thing I would like to mention is that between the GSI, which is equal to 75, let's say, and one which is 100, theoretically, you should not apply this GSI model. Just, I will describe this later as well, but in the original paper that describes this GSI model, it is said that if you have only few discontinuities and shear joints, you should not homogenize them within the GSI model, but model them specifically. So if I continue my design process here, I can compare these optimum results with the analytical model that was given, that I showed at the beginning, the Kim-Henshaw model, which is these black lines here. So as a function of the GSI, you have a different line. But what is important to observe here is that for this model, the deeper you go, the larger the capacity. And there is never, ever a cap in this capacity. So it gives the impression you can go very deep and keep increasing your capacity, while probably it's not. So using this approach, this numerical approach, helps the design and it's more confident. So now, this was a given anchor geometry, but we can do exactly the same process with a different anchor geometry. So the diameter of the anchor was kept the same, but in this case, so from this result to this result, the height of the anchor was reduced to 60% of the initial value. And this, you can see, doesn't change much the shallow part. So the comparison between these two lines, for instance, this is almost the same capacity for both anchors. But what does change a lot is this local mechanism here. So if you reduce the height of the anchor, you reduce quite a lot the capacity you can get, which means that the contact you have between the expandable fingers and the rock, and the height of this contact is quite important and should not be overestimated. Otherwise, you will overestimate quite a lot the anchor capacity. So this is a way of designing with Optum, and just create design charts, and then it is quite easy to pick the right value afterwards. Now, as I said just before, so this quote comes from the paper of Hook and Brum themselves, and said that if you have a sparsely jointed rock, so few joints, with respect to the size of the anchor or the tunnel or whatever, then you should not use the GSI model, which homogeneize the rock, the shear joints or the cracks or the fractures, but you should model explicitly the joints and use the Hook-Brown model for intact rock. So can we do this, or can we simplify the problem? Maybe we can. So it's just a very basic example. I just reused the same geometry in Optum, and since we can model shear joints, I just model shear joints as horizontal joints here. So obviously it's not a real case, because it's just this just considers that we have layers which are infinite and horizontal, which are not. But still, we can have some ideas of what will happen. So if we do this and run the simulation, this is the failure, well, this is a vertical displacement. This white line here was the previous failure mechanism we had, which was pure shearing. With this new configuration, we still have some shear failure here, but here we don't have shear anymore. It's more something like bending failure of all of these layers, which somehow makes sense. So it's a bit pushing very far the possibilities of the software, because since we don't have any shear failure, it's a bit more difficult to do the adaptive meshing, etc. So sometimes you need to refine the mesh here manually, and it's a bit more sensitive to the boundary conditions. But on the principle, this is something that you can do. And finally, if again you collect the load multiplier for a given geometry, the blue one, as a function of the relative embedment depth, was the homogeneous rock. And this curve was the capacity considering the horizontal bedding. So we have quite a large reduction here. So it can be worth explicitly modeling the joints to be sure that the capacity is what it is expected to be. Obviously, this is dependent on the spacing between the layers, and obviously you should have a lot of blocks rather than infinite layers, but still this is an approximation that could be done, and you could think about extending this to 3D patterns. Now, I mentioned that the loading will never be purely vertical. Actually, the mooring system will mostly be inclined. So we should consider the combination of horizontal and vertical loading for this type of anchor. The first thing to do is that there is no embedded Hook-Brown model in 3D. So you can do some approximation of the Moore-Coulomb model and use the tension cutoff here to approximate the Hook-Brown model by an envelope that is made of 2 straight lines. So this is what has been done. I think this is the basalt rock in this case. And at different GSIs, you can just refer to this reference to use the equations. So now we have these parameters. We can do the same thing as before. It's a very, very simplified geometry in this case. We have the pile here. We have a conical base because this is the specificity of this anchor, and we apply a unit load and just have a look at what happens. So this is what happens for a given geometry and a horizontal load. So we have the displacement, which is horizontal here, vertical here, and same for the stress, horizontal stress and vertical stress. So if you look at the horizontal stress only, it's displacement only, it's quite typical of a pile because obviously the rock here moves in this direction and the rock here moves in this direction because we have a rotation of the pile. But if you look at the vertical displacement, both sides are moving upward. So here you can have sort of a wedge of rock that is moved, which makes sense. And here, actually, you can observe that the rock is moving up as well, because actually, due to this conical base, when the pile moves laterally, the rotation is locked and the pile tends to move upwards the rock. So actually you mobilize a sort of uplift mechanism even if you apply a totally lateral loading here. While here it's purely a lateral mechanism with a rock wedge that is pushed laterally. And well, obviously, since here you are moving a lot of a big wedge of rock, you have quite large stress, vertical stress. And here we have horizontal stress, and we have horizontal stress that are quite large here as well. Now, what happens if we modify the inclination of this loading? So the scale is the same for all 3 figures, and the difference is that the load is purely horizontal here, slightly inclined here, 30 degrees to the horizontal and 45 degrees here. And what you can see is that the vertical part of the failure mechanisms on the left is more and more mobilized. And while here it was more or less a purely horizontal mechanism, as the inclination of the loading increases, it seems that the vertical part of the failure mechanism is mobilized on this side as well. And finally, there is some interactions. There are some interactions between the horizontal part and the vertical part. And in the literature, there are not so many things, there are not so many studies to predict this pile capacity. So there was this very simplified methodology in a PhD thesis, which basically only considers this wedge here. But since this anchor its rotation is locked at the base, there is no way it will just slide along its position, but it will be locked here. So this, although it can be used, needs to have some more refinements to be able to design this anchor in a very fast analytical way. If we do the same thing as before, we collect the load multiplier for all the simulations we could do for, in this case, I just varied the load inclination to the horizontal for different GSI. All the forces and the capacity is normalized with respect to this value. So normalization is a constant. This is the capacity of the anchor, which is loaded horizontally at a GSI of 100. So at 100, you can see that as the load inclination increases and moves from purely horizontal to vertical, then the capacity of the anchor decreases. And for a GSI of 20, it actually looks like very flat. But if you do another normalization, so you normalize each curve here corresponding to a GSI with respect to the initial multiplier, what you can see is that for the low GSI, the capacity decreases quite a lot with the inclination. So actually what happens is that, I think again with the pile, when you have a large horizontal component, you have this interaction between vertical and horizontal mechanism, and you increase the stress magnitude in the vicinity of the failure mechanism. So you increase the normal stress and you increase the shearing you can mobilize. While as this becomes more and more vertical, then obviously what the shaft induces becomes insignificant with respect to the failure mechanism, which is much wider and then much further away from anything induced by the shaft. Yeah, so this was for the 3D, and this is more or less the end of the presentation, so I can move to the conclusions. Firstly, since this is an Optum webinar, I can insist on the Optum advantages. For the purely design point of view, it's very helpful to do some fast calculations of the anchor capacity, and it's helpful to do some parametric studies. So when I say it's fast, it can be just a few minutes. So it's quite cool. From the research point of view, it was very cool to analyze the failure mechanism, the shape, but also the stress, because it's quite easy to access the different stress information, and then you can post-process it and compare to the theory. And also the software enables investigation of complicated geometries, complex rock structures, such as this rock bedding here. And it has the embedded Hook-Brown model, which is mostly used for rock mechanics. And it has a very robust interface elements. I used some other finite element software that were not that robust, and then simulations are much longer. If we focus on the main results for the groutless anchors now, so the focus on the project, then it's a bit of a tautology, but typical design methods for grouted anchors do not apply to groutless expanding anchor. So it seems obvious, but at least we have shown it. And we have also identified that the depth effect is very important, and especially the creation of this local failure mechanism that limits actually the capacity that you can mobilize for a given anchor. This is quite important in design. It is also very easy to generate some design charts for a given typical geometry, and it's quite easy to obtain this for different rock properties. And I think once you have done it once, it can be used as a quick tool to design the anchor for any project. Oh yeah, okay, we have this type of rock, so this is close to this value, and this GSI, so this is the capacity we get. From the 3D analysis, it's quite interesting to see that the uplift mechanism is mobilized also under purely inclined loading. So there are some interactions between them. So we were right to start by studying the axial mechanism before moving to the 3D, because actually they are linked. And with all of this information and all we have learned, there is definitely a need to develop some more adapted semi-analytical approaches for a fast design of this type of anchor. But this is another story, and this is for the future. And now, yeah, it's open for discussion.
Thank you very much, Benjamin. That was really, really interesting. Great presentation. Some really interesting results. I have some questions, but I think I'll take questions from the attendees first. I forgot to say at the beginning of the webinar that you can type in your questions using the Q&A button at the bottom of the Zoom window. There should be a Q&A button. So if you type those questions in, we will. I'll read them out, and Benjamin will answer them. So, first question: what is the required time for the optim runs for these types of analysis?
I don't remember all the time. It obviously depends on the number of elements, but sure. I think it's really few minutes, like maximum 5 minutes for a single simulation.
Yes, that's what I would say as well. But of course, it depends on the number of elements and
yeah. It was on my laptop.
Sure. That it's a question of the hardware as well. So,
yeah.
But yeah, a few minutes, and then of course with the upper and lower bound possibility, you have really the possibility to do some quality control, which you utilized as well quite well, I thought, because the question with these quite difficult analysis, Hope Brown is a difficult model to work with numerically, and interfaces and so on. You always wonder how good is my result really. But so the upper and lower bound addresses that issue. So there's a question here that was actually related to my own question. So you show that the capacity stops increasing at a certain depth.
Yeah.
So it sort of plateaus off at a certain depth, and that's a really interesting result, because it's one that's not necessarily very easy to replicate. I've actually tried myself with anchors in sand, where I would have some tests indicate that there is a plateau at a certain depth. Other tests indicate that it just keeps going. So it kind of just depends on the circumstances, but it's very difficult to replicate numerically this plateau. So and the question here is that one of the attendees has asked, where does the volume go for the deep failure mechanism? You have you need a conservation of volume down there at the tip of the pile in order for that local mechanism to form, right? And
yeah, I think initially in the initial design of the anchor, there was a bit more of a spacing here at some point. So you don't, no, I will go to another simplified thing. Maybe not in this one. So I think there is, here this is an idealized anchor, but you don't have necessarily the full contact all along here. So there was a bit of spacing. And I think since this is a rock, it doesn't need such a large displacement because it's super stiff. So it's more elastic, and then softening somehow. And I think even if you just let a little space here, it might be just sufficient to crack the rock. And once you have generated this local failure mechanism, then okay, you have a block of rock moving, but you will just move to a bit above it, where the rock will be sound again, and then you will create another failure mechanism. And I think in the end, you will just crack everything from here to the surface. But it's true that if we had something that was in very nice contact all along the drilled hole, probably this would not be generated as easily. But you never have a total contact all along. There is some, even for the installation, you have to drill a bit larger than what your anchor is actually, because otherwise you would be stuck. I don't know if this answers your question.
Yeah, could you show the mechanisms again?
Yeah.
So, Um, yeah, okay, so it's that one there, yeah. Is there any experimental evidence or sort of any experimental results that would point to things being in that way, that at a certain critical ratio of the height to the diameter there you plateau?
I don't think so. I think it's very specific to this type of anchor as well, because usually it's most of the experimental results that exist are for grouted anchors.
Sure.
And so it never happens.
Sure, sure. But this ratio H and D equal to 7 or 5 or in that range, is that where you are and for typical sort of dimensions, or you're above that or below that?
I'm not sure myself of what the answer is, and this might be something for the company to keep as a private thing, let's say. So I'm not sure, even if I knew it, if I could answer in the open this question, because
Sure.
yeah.
But it happens at some critical ratio.
Yeah.
So then there's a question that all these designs are based on the Hook-Brown criterion, right?
Yeah.
And another question is the bonding agents between the rock and the anchor. If it's not grout, what is it? I guess it's pure friction.
Yeah, but it's the whole point of this anchor, so we can see it properly here. What makes the anchor an anchor is that it is expanded laterally. Maybe if I go back to the initial figure of the anchor, we can see what happens. So you have the drilling bit here, and then at the end of the drilling of the hole, this part is moving upwards, and we have the fingers here that are expanded laterally. So you have this inverted cone, which is actually expanded into the rock, and then you cannot move it up because this base becomes larger than the hole then. And this is, so you don't need a bonding like the grouting. This is what creates the anchor. It's a bit like an underreamed anchor in soil.
Sure. Another question. So this is static. That's the static pull-out capacity. What about cyclic loading? Is that could that not so much doing the analysis, but the sensitivity of these anchors to cyclic loading?
Well, this is indeed the next question to be investigated. But we thought about it, obviously, but it was just a 4-month project, so we didn't have time to go that deep into the details.
Sure.
But definitely the rock, the cyclic loading will be important. So we ended up with a sort of simplified method to design this, because usually for rock, if somehow the stress loading, the cyclic stress is below 70% of the rock strength, you can apply 1 million cycle before, or millions of cycles before it fails. So what we just said is just, let's keep it below a certain threshold, and this should be okay. But we have not tested it nor modeled it yet.
Yeah, I think that's a very sensible approach. And if you wanted to do really cyclic loading, you would need a model as well. A more complete constitutive model rather than just sort of a strength criterion, which is a lot more complex, obviously. Interfaces, what are the conditions at the interfaces? I guess that's the Hook-Brown model is applied at the interfaces as well, or
I just used a more Coulomb for this one.
Okay, more Coulomb. Okay, with a certain friction angle, yeah.
Yeah. And indeed, the interface properties are quite important as well. So you can have some changes a bit in the depth at which you reach this deep failure mechanism, depending on the interface properties.
Sure. There's some questions on group effects. I guess you haven't looked at that, and for the application that we show here, I guess it's not exact. Group effects are not exactly that relevant either. I mean, these anchors would be fairly widely spaced.
Yeah. Yeah, the failure mechanism, especially the shallow one, being very, very deep, broad, sorry, you can imagine that there will be quite fast a group effect, but
Yeah.
this has not been tested yet.
Physical testing, is that, there's a lot of questions on that. Is that something, I guess that's something that would have to be done at some stage? Or
Yeah, I think the company has started to do some physical tests, or is planning to do some. But yeah, we have not yet compared everything that exists or not, and we will do it in the future, obviously. The problem for the load test that exists in the field is that, well, usually they are grouted anchors first, and you don't have much of information on the real failure mechanism. You just, what people did in the past usually was, they measured the force, the capacity, and then they thought, oh yeah, so we imagine we have this sort of wedge failure mechanism, and we know the angle, and then they deduced a stress along the failure mechanism, but actually you don't have any real information on what's going on really.
Sure. There's a lot of questions about the installation again. Now that you're on this slide, could you just repeat what you said about the installation, because that's quite unique for these anchors as well.
Yeah. Yes. So I think this is the drilling bit. So it's self-drilling actually. So you just, this is rotating, and you have the teeth here. So you just drill the hole up to the desired depth. And when you reach this depth, well, obviously you stop drilling and you just move this part. So I think this bit is going up. You have a nut there. So you just lock the anchor, and while locking it, these fingers are designed to be extended laterally actually by this bit moving upwards. And this is what creates the locking of the anchor.
Yeah. What are the typical dimensions of these anchors?
Oh, this is certainly something I'm not allowed to.
Okay. Yeah.
Actually.
Okay, but we have a picture of it here, so I guess that was a question as well. You can use your imagination. There's not a box next to it, but
if you have any specific questions, I added the website here, and at the end of the presentation, I added the website of the company, so you can contact them directly for this.
Yeah. Yeah. SME, sustainable marine energy. Yeah. Yeah. All the practical questions on the service life of the anchors in seawater and so on. Get in touch with the inventors of the anchor, SME, Sustainable Marine Engineering. Can this be used for soils? I guess if the soil is hard enough, it might be a possibility.
Yes, maybe, I don't know.
Okay.
I have some doubts about this, because if you imagine a soil, I think that this failure mechanism, very fast, you will just pull the anchor out with a tiny layer of soil on the side, because for a soil you would need really a plate or to mobilize really something. With this just slightly inclined conical truncated cone base, I don't think you will mobilize much resistance, but I'm not sure, so I wouldn't be definitive about it. I don't know.
Just a question that I'll actually answer myself. Do the interface properties influence the computational cost? I would say the answer to that question is no.
I don't think no.
The interfaces work, and they are, as Benjamin indicated, really quite robust. So they don't pose any problems. And
No.
I know a lot of users include interfaces even in cases where you don't necessarily strictly need them, just because it's not a bad thing to have. So you can have interfaces with the same properties as the surrounding soil, so that will just sort of increase the accuracy of your solution. So interfaces between the foundation and the soil, for example. So it's something that doesn't influence the computational cost at all. So I think, and the interfaces, as Benjamin indicated as well, were more Coulomb. So with a friction angle and zero cohesion, I guess. So for purely frictional interfaces, you could have applied the Hope-Brown model as well. I mean, so you would have, so an interface in Optum is just basically a very thin layer of material.
Yeah.
The same properties material-wise as the soil, surrounding sort of soil. So you can apply any model to the interfaces. And more Coulomb is, of course, when we talk frictional interfaces, an obvious one to go with. So I think that's it. And I would like to thank you again, Benjamin, for a very interesting presentation. And thanks to all the attendees for taking part and for your questions. We will be running another webinar next Thursday. Details about that will be sent out, along with the link to the webinar here as well, to the recording of this webinar here. So
thank you.
Thanks again, and see you next time. Bye.